Right, we're just continuing on this list that we were working on before. So we're just going over the heat idea and the fact that it does change the value for K, and of course it goes through a shift as well. Next one on our list is if we reduce the volume of the container, think gases. If we reduce the volume of the container, the reaction moves to the side of the reaction with less moles of gas. So for example, say you've got 2 moles of gas over here on the left side, and I have 3 moles of gas over here on the right-hand side. And the container in which this is in, I decrease the volume. And if I look at it decreasing the volume, which takes up less space, these are all gases. Well, 2 moles of gas takes up less space than 3 moles of gas. So the reaction will actually shift to the left-hand side because 2 takes up less space. Just the opposite. If I make the container larger, it can now accommodate more moles of gas. So it'll shift to the right, over to the 3. Okay. Continuing this thought, let's look at the last one I have here. Actually, the second from last one. If we add a non-reacting gas, think of a noble gas like neon or argon, you will have no effect whatsoever. So when you add a non-reacting gas, remember the law of partial pressures, they all just kind of behave independently, so it doesn't even seem as if it's there. So there's no effect at all. So if we add a non-reacting gas, no effect. Last one we'll put on this list. If a catalyst, catalyst, I don't know why my Y came so soon. If a catalyst is added, both the forward and the reverse rates increase. So it's faster to the right, faster to the left. But no change, again, in the K value. No change whatsoever. It goes faster both ways, but the value for equilibrium constant stays the same. All right, let's bounce back to this top problem we were looking at the beginning, and we should be able to take this on a little more easily. We have this expression here, and I'm going to suggest that can we make this reaction move, or will it move? If I only have in the container, the only thing that's present is calcium carbonate solid. My question would be, will it move? Will it establish equilibrium? Will I get a full equilibrium, allowing just this to be present? And the answer is, drumroll, yes. I have all of the reactants present. That is the only thing that is necessary. It'll degrade and form these 2 products, and I've got equilibrium. Done. Next question. I have calcium oxide, solid, and carbon dioxide, gas, present at some pressure greater than Kp. So the question is, will I establish equilibrium? I've got both of the products present, and my pressure is something greater than carbon dioxide at Kp. Will I establish equilibrium? And the answer is, I didn't write in the first one, I'll do that now. Yes, you will establish equilibrium because my Q, if you will, is too large. I need to shift in the other direction to alleviate that pressure. So I will form more of this, and this will go over to the other side as well. I will shift to the left to re-establish equilibrium. These are tricky questions. You probably have to go over them once or twice. C, calcium carbonate is present and carbon dioxide is present at a pressure greater than Kp. Will I establish equilibrium? And the answer is, surprisingly, no. Now, you may think, well, yeah, because it wants to go and I need this to go. But unfortunately, I have to have both of the reactants or all of the reactants, or excuse me, in this case, products, both of these products present in order to shift in that direction. I only have the one. This cannot decay on its own and form this because the pressure is inhibiting the decay over in this direction. So the actual answer is no. So, and just to add to this, we need calcium oxide present. We don't have it. Last one on here, you have present calcium carbonate, solid, and calcium oxide, solid. That's the only thing in the containers. Nothing else is present. And the answer for this one is yes. And the reason is I don't have any of this to inhibit it, so there's like a vacuum, if you will. The calcium carbonate will decompose and form additional calcium oxide. I already have it, but it'll form additional calcium oxide and form enough carbon dioxide to form the pressure necessary to establish equilibrium. Done. All right, let's shift over to some problems. So we're looking at 39. For number 39, you have a mixture of carbon dioxide, you've got some hydrogen, some water in a container. The following equilibrium is established. There it is. Okay. Calculate the initial pressures of the three gases. 1, 2, 3, or excuse me, 4 gases. But it's only asking for 3. All right. So if I'm looking for pressure, what I have to take a look at here, and many times when you look at an equation, it just gives you a bunch of stuff. It's probably a Inert problem. It doesn't have to be, but it probably is. I can look at these all individually, and I will, because it asks for the partial pressures of all of them. So doing the partial pressure of CO2, I'll have 0.2. That's a terrible looking 2. Sorry. 0.0821. 500 kelvins. I'm not writing the units in, but just make sure it is in kelvins. It has to be. And this is 2 liters. The value or the answer for that one is 4.1. These are ATMs. They're all ATMs. The pressure for the hydrogen, 0.1, 0.0821, and 500. 2 again, and that is 2.05. And then the pressure of the water vapor, 0.16, 0.0821, 500. And 2, that gives me 3.28. Okay, that part's done. At equilibrium, the water pressure has a pressure of this. Calculate the equilibrium partial pressures of the other 3. So, All right, well, I guess if we're going to look at this one, we have to do something that we haven't done up to this point. Let's take a look.